In the last 2 weeks, we considered a case. So we study perturbation theory, time-independent perturbation theory. Okay? So in the time-independent perturbation theory, the main question is to find, in an approximate way, the eigenstate and eigenfunctions of an Hamiltonian which is slightly perturbed from some unperturbed Hamiltonian which we know how to solve. Okay? So if we know everything about some Hamiltonian H0, when I say everything, we just know the eigenvalues and eigenfunctions, then we know in principle how to compute eigenvalues and eigenfunction of an Hamiltonian which has a small term lambda v. Okay? What does it mean small? So it's not lambda should be much smaller than 1 by itself. Okay? So small means something that we discussed in the previous lectures, and this small means also that we have to distinguish between the casing of non-degenerate spectrum to the case in which we have degenerate spectrum. Something which I stressed, I hope I stressed, but I would like to repeat, is that the application of non-degenerate perturbation theory or degenerate perturbation theory is not something that applies to all the spectrum. Okay? There can be cases in which a part of the spectrum is degenerate, some other part is non-degenerate for some reasons I don't know. Okay? So depending on the case you are studying, then you have to decide which kind of scheme you have to apply. Okay? So once you finish the exercise that I assigned you 2 weeks ago, then we'll proceed and we do even more complicated things. Okay? Now, today I just would like to discuss the third topic in perturbation theory, which is important to go through, that is time-dependent perturbation theory. Okay? So time-dependent perturbation theory faces the problem and trying to understand what is the time evolution of a quantum state. Okay? In the case in which you know a starting point which is known, but then you add some perturbation. Okay? So we just consider the case in which the Hamiltonian splits in 2 parts again. So H0 we just take it for simplicity, time independent. Okay? So in principle we can even generalize, but the important thing is that we know everything about H0. But we consider the case in which H0 is time independent, but then the perturbation that we are adding will depend on time. Okay? So differently from what we studied in the previous weeks, then we are just putting V of t. Now, the main, as I said, is that H0 is time independent, and we suppose that we know what it is. Okay? So we know this phi 0. And we will use this as a basis.
Still non-degenerate.
We'll do it non-degenerate. Okay? But since you understood what is the trick, if it's degenerate, that is not, it does not match. Now, when we do time dependent, there are several different cases that we should consider. Okay? For the moment, we will analyze just perturbation theory in lambda. You will see later. Okay? So, what is the main new ingredient that we have to face here? Now, the full dynamics is governed by a time-dependent Hamiltonian. Okay? So, therefore, it does not make any sense to discuss about eigenfunction and eigenstate of H0 plus lambda v. Okay? So, in the previous case, so we had eigenstates of the Hamiltonian of H0, and we wanted to determine the eigenstates of H0 plus lambda v. Here it does not make sense. The full dynamics, we have to study the time-dependent Schrodinger equation. Okay? So the thing we have to understand is how to construct the time dependence starting from a knowledge of this basis. Is this clear? Okay. So let's see. The first thing I would like to know is, suppose that we have a state, so let's consider first the case in which lambda is equal to 0. Okay? Then, suppose that you have an initial state which is phi of 0. Okay? Now, so I'm considering this case, okay? So, can you tell me how to write the evolution?
The evolution operator has to be...
No, yes, but using this basis.
E to the negative IHD over H bar phi 0.
Yeah. So, you say this is e to the minus I over h bar h0 t phi of 0, right? Good. Now, I told you what is phi 0 of n, the eigenstate of h0. Can you write this in terms of the basis?
Yes.
Okay, how?
It will be sum from sum all over n indices.
So this I can write as a sum over n.
E to the IH E of n.
Okay.
And then there has to be bra psi n 0, and the coefficients have to be taken from the
So this will be phi 0 n here.
and Cn.
And here I should put
constant.
Cn of 0.
Yeah.
Okay? And what is Cn of 0? This is what?
The scalar product of phi 0 and phi n.
Okay? Huh? Okay? How do you get to this point? So the answer is correct. Okay? So
First of all, we expand phi of 0 at 0
so
time in the
you
basis
can expand phi 0 as sum of n Cn of 0 phi n of 0. Okay?
and then apply.
So you just write using this basis, but then we know that e to the minus I h0 over h bar t applied phi 0 of n, since these are the, okay, so I think there was a line here, right? So this is just e to the minus I e0 n over t over h bar phi 0 over n, right? And then we get this. Okay? Very good. So,
I am a little confused. This is psi, right?
which one?
The second line on the left, and then on the right it's 5, 0.
Yes. So I have the initial state, which I call phi 0. Then I apply the unitary evolution, and this gives me the state.
Phi of t, it has to be phi of t.
Can be whatever, I mean. Okay, I want to confuse. Okay, I don't call it phi of 0, I just call diploma. So this is my initial state, diploma. Okay? It's a spatial, so there is a basis of 8, okay? So it's formed by an 8-dimensional Hilbert space. How does it evolve? To the final crash, which will be the exam. Okay? So this we call it whatever we want. I mean, I want to use this just to that you understand the. Okay? Then this we can call it diploma of time t, whatever. So I just use the same definition here. Okay, I just say that the quantum system time t is in the generic psi of t. Okay? Then I just say that psi of 0 is defined in this way, whatever it means. I'm just fixing as an initial condition. Okay? Then in order to determine psi of t, I have to apply the evolution to the initial state. Right? Is it now clear or? Okay. Now, what happens if the initial state diploma, or it's not diploma, but is phi 0 or 1? Okay? So, if the initial state is one eigenstate of H0, what happens?
It will be E of 1.
So the states will be always phi 0, 1, and there will be only a phase winding. Right? Because in that case, this scalar product will be just a delta function, a Kronecker delta. Just as it will be 1 if this n is 1 and 0 otherwise. Right? Huh? So this means that once we are looking for time-dependent problems, then unless we start with an eigenstate of the Hamiltonian that we are considering, in general, even a time-independent Hamiltonian will generate some superposition. Okay? Yes? It's okay? Good. Let's make a very simple exercise. Okay? So we consider a two-level system, okay? And so this is exercise. So what do we choose as a basis? We choose up and down along Z, okay? So I do not write Z, okay, but you keep it in mind. So I prepare the state psi of 0. I just prepare it in up plus down. Okay? So this is t equals 0. Then I just apply, so I'm considering a very simple exercise with time dependent, and the time dependence is particularly simple. Then from t equals 0 to t equal t bar, okay? So the Hamiltonian H0 will be omega 0 sigma z. Let's say H bar. Okay? So what is the state at time psi of t? At time t bar. This is a question, so you're supposed to answer. What is? I would like to know what is psi of t bar.
1 over square root of 2.
This is the easy part. Huh?
Then e to the I omega over 2t.
Up.
Omega t
2
2 what
over
is
2. Okay.
Let's consider the over 2 is
One
okay, but let's consider just okay times up, plus,
It has to be down if it matters at all.
For the up, it should be negative I omega not t.
And I to the plus omega 0 t and then.
okay. Then from t bar to twice t bar, the Hamiltonian is h bar omega 0 sigma x. Okay? So this the Hamiltonian is time dependent because I'm changing the Hamiltonian. So what is the state at psi of 2t bar? So I start the easy part, 1 over square root of 2. Okay? Then I can write e to the minus I omega 0 t bar. Sorry, here there is a t bar.
2 t bar.
Huh? No, I just wrote this exponential. This exponential is there. Huh? I just rewrote this phase factor. Okay, this phase factor does not change. So the only thing you should tell me is that how this will modify h, so up.
Sigma spin up is not eigenfunction of sigma x.
Exactly.
So with up and down has to be rewritten in terms of up and down in x direction.
Exactly. Very good. So you see that I can write up along the z direction as a 1 over square root of 2 of up along x plus down along x. Okay? And if I could just put down, this is a minus sign. Okay? So you just substitute. Let's start. Let's do the first thing. So this up is just this. So what should I write?
Extra 1 over square root of 2.
So there is a 1 over square root of 2, which is 1 over 2, okay, because it will be everywhere.
It will be e to the minus I omega 2 t bar up in x.
No. Yes.
Then plus exponent with minus sign down x and
Huh?
omega 2 t bar down x.
Is it correct?
Seems like.
So he said yes, because
No, I said seems like.
seems like. Okay. Does everybody agree with Michael? Let's see who are the friends who are not the friends. So do you agree?
I don't understand why there are two exponentials
Yeah.
inside of
Okay.
each other.
So here and here.
Yes.
Now, the first exponential is just this, okay, which was there. It was a coefficient that I have to write here. Then I have the state which evolves, and we can propose this, okay?
Not really.
No? So,
The time evolution from time t
not
bar
really, you
from-
did not propose, or,
no.
or you're changing your mind?
Shouldn't be the evolution operator defined in a bit different way? Since it's
Yeah, no, so this is my question, so it's up to you to tell me. Look, it's good, it's showing intelligence to change your mind, okay? So I think you are allowed to change your mind.
Is it starting from T to T bar from
Very
T
good.
bar?
So we have to include the interval
Yeah.
between T bar and 2T bar. So what should I remove here?
2.
2.
Yeah.
Okay? So you continue and then you will find something. Okay?
I don't get why we should continue.
Oh, because I wrote only this part.
Yeah.
Then I should write, okay?
Yeah.
But it's a repetition, so the only thing which changes is that here we have a minus sign, then you collect everything. Okay? If you want to write it in a basis of z, then you have to go back, instead of using this up x, you just invert this transformation, you write in terms of up and down. Huh? But it's a choice of a basis. You can do whatever you want. Huh? But you see that in general, if you start with a state which is not an eigenstate in the presence of, so here we consider even a time-dependent Hamiltonian, then the state evolves. Okay? So don't talk about eigenstates of a time-dependent problem. It does not make sense. Okay. Can I give you a difficult exercise? Yes. Yes. I do it for you because then you will be very happy once you solve it. Okay? Now, do the following. You have an harmonic oscillator. The nice thing is that I'm inventing this, okay? So I hope it can be solved. But you will suffer. I'm relaxed. Okay? But if you prove that there is no solution, it's quite... No, I think it can be solved. I'm joking. So suppose that you have an harmonic oscillator, okay, with a trap of a particle in an harmonic trap in one dimension, okay? And suppose that the harmonic trap is omega 0. So you know everything, you know the, okay? So the mass, you know the trapping frequency, so you know how to write the Hamiltonian, okay? And suppose that the system is initialized in the ground state. Okay, what is the wave function of the ground state? It's a Gaussian. Okay? Good. At 0, at the initial time, the trap is open. Okay? So, and it is open in two different ways. The first case in which the trap is open in such a way that it is open, so the trap disappears. Okay? So, it's like you trap a particle, okay? And the particle is in the ground state. Then at time 0, you take it as initial time, it's open, so it's in free space. What happened to the particle?
The ground state dissipates into plane waves or whatever it is.
Yeah, well, we don't know, but the particle will spread,
Yeah.
right? So it's not trapped anymore, it's spread, right?
Yeah.
So you have to describe how the probability changes, the probability to be in a given position. So you just put the trap in 0, okay, in x equals 0, center around 0, okay? How the probability to be in position x change with time. No, it's open, it's flat, it's not even...
Just
Yeah. Okay? Now, this is a good exercise, but in order to make you happy, you can solve even the other exercise in which instead of being open, the trap becomes omega 0 over 2. So just open, but not, that's why I told you to eliminate this, okay? Because this is a case in which it goes to omega 0 over 2. Is it okay? Clear? This second part is very difficult. I don't think you will manage to do all the calculations. Okay? So I don't care, but I want to see that you write down the integrals in a meaningful way. Okay? But this does not mean that you don't have to write the integrals in a meaningful way. Okay? So I would like to see a result which is a very complicated integral summation whatever which takes 6 pages, and then I say I don't know how to compute it. Okay? But I want to see it right. Questions? Huh? Is the problem clear?
So at time, if the initial time equals 0, it is flat.
Yes.
And then at some later time t, we're just going to evolve it with a flat, or is the potential gradually dropping it?
No, there is no gradual. So it's sudden. In 0 time. Okay?
Okay.
So this means that for time up to t equals 0, then the Hamiltonian is the harmonic oscillator with frequency omega 0. At times t at 0 plus, so epsilon further, the Hamiltonian is either free space or an harmonic trap with omega 0 divided by 2. Okay? Now, the third question for both cases is, after let's say after a time t bar equal to 10 pi over omega 0. I put h bar to 1, okay? So just fix it. I would like to know the energy of the particle, the energy of the particle. In both cases. Now, for this third question, you should think. So you should think in general, okay? But for this third question, if you try to solve it brutally, so you're really doing the calculation, then I will see you in 2 or 3 years with the solution, probably, okay? But if you understand the meaning of the question and the problem, then you will find the solution like this. So you have to think for 6 hours and then you find the solution like this, okay? It's not that it's immediate. You have to think. I mean, there is some pitfall hidden in the question, okay? I'm making your life more complicated than it is. Clear? This means that you owe me how many exercises?
3-ish.
So last week was 2 exercises or 1? I forgot.
Just 3 equals 1. 1 ABC.
You're kidding me or you're sincere? It was 1, but it was ABC. Okay. So 1 plus 1. Okay?
When do we have to submit
Today. Okay? You see, you should not ask questions if, the right question is that, is it okay if I send you by Friday, January 21, 2026? That's the question, because you encourage me to, So there is a very nice book, very interesting book by a Nobel Prize winner, which is called, we are recording, okay. Okay, this is out of the course, but if you are curious, then you can read this book it's called, so the author is Kahneman, and it's Thinking Fast and Slow. It's in English, so the guy is a cognitive psychologist, and wrote a book. He just made a lot of experiments, and actually he got the Nobel Prize in economy. And one chapter is about this. When you start a conversation, so this is, for instance, applies to those people that negotiate things like real estate or something. The way you start, it gives you some advantage. So it seems that if you start by saying, I will bring the solution by 2025, then I would say, no, this is not good, let's do it 2021, which is already something that you get, right? But if you start saying, I should decide, then probably I have some small advantage. Okay. So we agree that you send me the first exercise by Wednesday, and this by Friday? Huh? Morning? Friday. You just Friday, okay?
Would this be like an atom or something in an optical trap that when you put the laser on it's there and then you put it off it just vanishes?
No, this is a laser is something which is time dependent, so we will do it later in a sec. No, what we are going to do about time dependent will be related to this, because we are going to study the case in which you apply time dependent in such a way that you induce transitions. So basically you study that if you apply some periodic perturbation, then you may induce transition between levels, right? And you know that you have to choose carefully the frequency, right? Such that if the frequency is on resonance with the level splitting, then you will induce transition. If it's off resonance, you don't, right? You know this or not? Just tell me, yes or not? No. So do you know, so if I apply, so do you know what is a transition between levels in an atom? Huh?
Okay, I think we know this.
So you talk on behalf of everybody?
I think you're talking
So I have to give you a very bad news, okay? Now, when the teacher speaks and the students do not want to answer, they avoid eye contact, okay? This has been like this since the prehistory of... Now, you are 8. It does not work, okay? So it does not work. So you can continue to look at me. It's nice, so that we just look at each other and I will not be... So, but if you try to avoid to look at me, it will not save you. Because if you have 600, then I can get trapped in somebody who's talking to me and get distracted. But here, I can scan the room, 600 times per second, okay? So just relax, continue to look at me, and we continue to discuss. Okay? Eye contact. Now, do you know that if you have a level and you want to, if you have an atom in a given level and you want to induce a transition to the first excited state, hydrogen atom, what do?
Shine the light.
Shine light. Okay. So how do you choose the light that you want to shine?
The energy
The
of photon.
energy should be equal to the gap.
The frequency.
Yeah.
Which is exactly what I said 2 seconds ago, right? So why do you choose this? If you choose that is 6 times the gap, what happens? Huh? Now suppose there are only 2 levels, okay? So,
because of the L.
now first I want to know what happens. Then you tell me the because. So suppose that you have, so forget about the higher levels, okay? So you go from the ground state to the first excited state. And this is the gap and you apply the right frequency, you have a transition.
Yeah.
Now if you choose a different frequency, by mistake, what happens?
No transition.
No transition. So if you start in the ground state, you will roughly continue to stay in the ground state. Do you know this? Do you know this or not?
Yes.
I think it's not that straightforward to say this.
No, I'm not asking if you are able to tell me. I'm asking if you know it. That is different. Huh? So do you know that the concept of resonance condition?
Yes.
That you have to tune the energy or the frequency in such a way to go on resonance with the level transition.
Yes.
Yes.
Okay? Is this known or... Okay?
Yes.
Yes. So this is what we are going to study. Okay? In the bar, you know that there is in Trieste there are 50 different types of coffee. Did you notice? If you go in the bar,
Yes,
there is a poster. Okay? So we should also try the same thing with 50 different ways for students to say I don't know, which is yes. And all this type of different variation. Now, in time-dependent perturbation theory, in general, when you apply a time-dependent Hamiltonian, even if you prepare the system in a given state, this will in a given eigenstate, for instance of H0, this will change. I mean, okay, it will not remain in the eigenstate because the evolution will make the state evolve and in a generic superposition of phi 0. Okay? So we are analyzing first the generic situation, and then we will consider different cases, okay, which are of particular importance. One of those cases is when you apply a time-dependent perturbation. A periodic perturbation. So what are the other examples of resonance you know in physics that you studied the first year?
Like the oscillator which we
Yeah. So if you have an oscillator and you apply a frequency, a driving force which is periodic, what happens?
If the frequency of the drive,
What happens over there?
For example, with like the string of a guitar.
Yes, any harmonic oscillator.
So for example, if you pick the string, then you will have all the different frequencies, but the frequency that at the end survive.
No, I'm asking a different question. Suppose that you have an harmonic oscillator, a given frequency, okay? Then, if you just apply a driving force, which is periodic, okay? Then, what happens to the harmonic oscillator?
If the frequency of the driving force is equal to the frequency of the harmonic oscillator, then they will oscillate in resonance.
Yeah, what does it mean, resonance?
Highest amplitude.
Very good. So, the amplitude of the motion will depend also on the drive, so not only on the amplitude of the force, but also on the driving frequency. Okay? So if I give you some small, so when you go to this is a different, so let's not do it. Okay? But so you can get a big response if your periodic perturbation is chosen with the right frequency. We should match some internal frequency. Right?
Yes.
Huh?
yes.
No. Nadine? No? Okay. What? So you tell me. Tell me what is no.
I can't remember what we were talking about.
This? Okay. So, Nadine? Do you remember at least or no? We are on the same...
So is it like the Tacoma bridge that fell down because it got the right frequency?
Yes. So, I would like to ask you if you what you remember of the concept of resonance. Okay? Which was said... so, if you have an harmonic oscillator, which oscillates with the frequency omega 0. What happens if you apply a driving force which is periodic? So I propose the following. Those you don't remember, just go and get. So it's in physics 1, so just resonance. If you look, mechanical resonance. Okay? Because we are going to see a phenomenon which is very close to that one. So that we see that the response of the system will be enhanced when the perturbation, the periodic perturbation, is chosen with the right frequency. Okay? The one of the Tacoma River, it was a mechanical thing. Okay? Now, last half an hour, let's see the theory of time-dependent perturbation theory. So I want to study this problem, okay? And I would like to use this as a basis. So what I would like to do is I want to write the state psi of t using this basis. Okay? So following the example that I gave you before, I just write this as sum over n of c n of t e to the minus I e 0 n of t over h bar phi 0 of n. This is a choice. So I don't know what is the coefficient. I'm just choosing this as coefficient, as a way to parameterize any state. Is it okay or not? Okay. Now, the fact that I put here exponential or not is irrelevant. So it is a choice. You can also write this as a sum of n c tilde n of t phi 0 of n. Okay? It's the same. So I'm just saying, I'm just taking any state, I can just write as a linear combination of its superposition with a basis. You will see that if you put this here, it's more convenient in perturbation theory because the equation simplified, but it's not really important.
I have a...
Yes, go ahead.
Shouldn't the Cn depend on the initial time, so let's say time t?
Now the Cn, they will depend on the initial time and on the evolution. So now the question is that I want to determine this. Okay? So, yes.
First of all, we are writing the initial state of the system as a superposition of the Cn's with the
No. This is for any time.
Okay.
So what I'm saying is the following. I would like to find. So let's do the following. Do you agree that I can write any state in this form? Because it's just like in any vector in components. Okay? Now, if lambda is 0, what is the value of Cn? This is what we did before. If lambda is 0, then Cn of t is just phi 0 n psi 0, okay? The initial state. It's a complex number, it's time independent. Now, if lambda is different from 0, we don't know. We have to find these coefficients. Okay? This is the thing we would like to solve. So if we use this as a basis, then we can write down the time-dependent Schrodinger equation as a set of differential equations for the C, for the coefficients. So if you use this decomposition and you plug it here, then so what you have to do is the following. You just take this psi of t and put it here. Then you do all this derivation, you apply h0, and then you multiply from the left by phi 0 of n. Okay? Then you will find this equation. So you find I h bar d dt of c n of t is equal to lambda sum over m of phi 0 of n v of t phi 0 of m e to the minus I e0 of n of t minus of t e0 of n times t over h bar c m of t. What does it mean this? This is nothing else than the Schrodinger equation for the components Cm. Is it clear or not? Huh? Okay, explain what I know, what I did. Just imagine the following. So suppose I want to study a generic vector, okay? Okay, I do it here. Suppose that you have a generic vector r of t, a vector which depends on r all time, okay? Suppose it's two-dimensional vector. This r of t will be something like x of t. So I can write it as a component, okay, along x and along y. Okay, and these are the unit vectors. So I can express either an equation of motion for the vector r, or if I choose some basis, then I can write a set of equations for the components. Okay? So this is the Schrodinger equation for the state. If I express the state through a given basis, the only thing I have to specify is that the equation for the various components. Okay? And the various components are this one. Now, just verify that this is the correct equation. You just do it yourself. And for instance, verify that. So I just say it, but you just check yourself. When lambda is equal to 0, this is just dt of Cn is equal to 0. What does it mean? It means that all the coefficients are independent on time. So the one that you determine at t equals 0 are the one which remains like this forever. Now, since there is a perturbation, this is not true anymore, but this is the equation that they have to obey. Now, why do I like this expression in this way? I like this expression in this way because you see that here there is lambda, so I can construct the same perturbation expansion as before. So I just say, look, but Cn of t I can write as C0 n of t plus lambda C1 n of t plus lambda square C n of t plus da da da. Okay? So I just look for a solution which is perturbative in the parameter lambda. So when I substitute, then I will get that on this side I have I h bar d dt of C0 of n plus d dt lambda C1 on n plus lambda square C2 n of t plus da da da. Okay? This will be equal to this, where instead of putting Cm of t, I just put Cm0 of t plus Cm1 lambda and so on and so forth. Okay? So since I'm looking for a perturbative solution, then these terms should be equal term by term. Okay? So let's see what is the first term.
Sorry, is
Yeah.
the sign in the exponential of this equation positive or negative?
Where?
The exponential.
Here?
Yes. I mean the first.
Yeah, so it's positive. Because this should go for a minus sign, yes. I think I can check it. Yes. Okay? So the next step is that I equate the coefficients term by term. So let's consider the zero order coefficient. I get dt of C0 n of t equals 0. Okay? So, because this is already first order. Okay? So, the left hand side, the zero order is this one. Here there is no first order. And this is correct because you see at zero order, this should not be dependent on time. Huh? Then I have the second order, the first order, which is d dt of C1 of n of t is equal, so I just write I h bar. I shall substitute this, where I just put only, so this is 0, sorry, the C0. Huh? So I have sum over m 5 0 of n v of t 5 0 of m is I h bar this okay? And then you continue like this. So you do it, you just write the second order. Okay? So the second order will depend by the previous. Now, you do it yourself. Huh?
We need a lambda in.
No, because there is lambda here and lambda here.
Okay.
So just simplify. Okay? So you need to restore lambda in the solution. But the equation doesn't matter. Okay? Now, do you see that there is a similar structure as in the time-independent case, that you solve the first equation, you put it in the second and the third. So it's an iteration. So perturbation theory simplifies your life in the sense that you go by iteration. So this is just a huge system of equations. Okay? This one, you just solve it by iteration. Huh? Now, we should understand what you can learn out of all this. Okay? So I just removed this. By the way, can I give you a suggestion, a serious suggestion? So some of you already wrote the exercises in LaTeX. Okay? I don't remember who did it, but it was a good choice because this first forces you to be much cleaner. Do you know LaTeX? Okay. So I would suggest that you prepare just one file and then you add exercise by exercise. Okay? You just write number 1, you just put the text and solution or something. Don't generate 600 different files. I mean, it's fine because, it will not take much space, okay? So you can send me always the same big file and I know which one. So you just put the number or the date or you choose some enumeration, okay? And so that at the end of the course, you have a small booklet of exercise, and especially when you have to just go through the course and then for preparing for the exam, I think this will be more useful for you. Okay? If you don't want to do it, don't do it. Okay? So you can do whatever you want. So I will read it if you write on pen or whatever. This, I think, it's better for you just to keep all the information together. Huh? Now, so let's see the first solution. So the zero order solution, we know what happened. So the first order solution, so suppose that you start from a given state. So suppose that you start, so you see that you have to specify what is the initial condition. I think you asked about the initial condition, right? So let's suppose that the system initially starts in a given state, say in the ground state, or some initial state. So if it starts with the initial state, this means that C0 of M is just delta Mi. Because we said that C0 does not change in time. Okay? So even though here there is T, it does not really matter, because we know that C0 of M will be just the C0 of time 0. And let's suppose that I start in a given initial state. So that Cm is just 1 or 0. Okay? So So then you can integrate this.
What is the I index?
Just give an index, initial. So just n goes from 0 to infinity or whatever, you just choose a given one. So you can call it n bar or something, okay? So just take a specific one. I'm just calling E because in the notes there is E, so that you can easily check. Okay? Now, this means that C1 of M will be equal to 1 over I h bar, the integral between 0 and t of dt prime of v n I of t prime e to the I omega n I of t prime, where v n I of t prime is just this scalar product, okay? Phi 0 of n v of t prime, phi 0 of I. And this is just omega of n m, okay? So you see that because of the time-dependent perturbation, then as the time passes, then this, say this C1 at the beginning were 0, unless m equals equal to I, then will become populated. So you will start having transition to the different states. Yeah? Now, what is the probability that I go to the states n different from I?
That's order.
Yeah, no, tell me first. So my question is that I would like to know what is the probability of being in I, no, so in n. So if I go from I to n different from I at time t. Okay?
In terms of C coefficients or weight functions?
Whatever you want. So I want to compute it, so
It has to be,
it should be the square. You say that. So just I want to know the formula, okay? So this I just erased the. So if I use that, the composition of the state in terms of Cn, okay, what is the probability that the system is in the state n?
The square of the C.
Huh?
The square of the C.
Oh. So here it's just C0 of n of t plus C1 lambda of n of t plus squared. Okay? What is C0n? We said that n is different from I.
It should be 0.
It's 0 because we said that this. So this is 0. So this is the probability to go to a different state, not a higher state. It's just C1, so lambda square, C1 n of t squared. Okay? So you take this and you square it, and this is the probability. Okay. So, exercise. Suppose that the system is in the ground state of an harmonic oscillator. Okay? So you know everything, H0, everything. And then you put lambda V of t, which is equal to Q epsilon x, the epsilon operator, okay? This is the position. So I would like to know the probability that the system goes in an excited state as a function of time.
Any